So I actually don't have any text on these slides. These are mostly just to remind you what to talk about. So first topic is binary conversion. So in our class, we discussed converting to and from binary with decimal, and we also discussed converting to and from hex. So on the AP exam, you will only need to be able to convert to and from binary. In previous years, hexadecimal has been on the AP exam. This year, I do not think it is. To my knowledge, hexadecimal is not on the AP exam for this class. It was something that we learned, something that is useful, but it will not be tested on the exam. So the only conversion that you need to be able to do is to and from binary and decimal. So let's do a brief recap of our different number systems. In decimal, our number systems, or our number places, our digits go from right to left, or left to right in order of size. So we have our 10 to the 0 place, 10 to the 1 place, 10 squared, 10 to the 3rd, etc. And then we can have any digit within each of those buckets. 3, 9, 1, 8. That's not what 8 looks like. So we multiply the value of the digit by the value of the place. We add all those together, and that gives us the number. So 8193 gives us 8 times 1000, 1 times 100, 9 times 10, 3 times 1, which is 8,193. Pretty simple, pretty straightforward. Binary uses that same idea. However, our base is, instead of 10, our base is 2. So our places are 2 to the 0, 2 to the 1, 2 squared, 2 cubed, etc. And our digits, instead of going from 0 through 9, because that gives us 10 digits, here we have between 0 and 1, which is 2 digits. So in each of these buckets, we can have either a 0 or a 1, 0, 1, 0, 1. And this, we're going to convert in the exact same way. We're going to multiply the value of the digit by the place. So 1 times 2 to the 3rd, plus 0 times 2 squared, plus 1 times 2 to the 1st, plus 0 times 2 to the 0. And we convert our exponents to actual values. We have 1, 2, 4, and 8. 1 times 8 is 8. 0 times 4 is 0. 1 times 2 is 2. 0 times 1 is 0. So the total here is 10. So if we convert from decimal to, or from binary to decimal, we get that number 10 in base 10. So 1010 in base 2 equals 10 in base 10. You with me so far? Remember how to do conversion with binary? You want to do another example? Another example, all right. So let's do a longer one this time. Let's say we have 1, 1, 0, 0, 1, 0, 1, 0. I mean, it's just that 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So I think 8 digits is the most you're going to have to calculate. Now let's talk about what places we have. We still have 2 to the 0, 2 to the 1, 2 squared, etc. So let's talk about what those numbers actually represent. 2 to the 0 is equal to 1. We multiply that by 2, we get 2. Multiply that by 2, we get 4, 8, 16, 32, 64, and 128. So those are our first 8 places in binary. Those are the ones that we are going to work with. So to convert, we are going to multiply once again the value of the digit by the value of the place. So fortunately, we're only multiplying by 1 and 0. So we're essentially just going to add up any of the positions that have a 1. So 128 plus 64 plus 8 plus 2. 128 plus 64 plus 8 plus 2. I can do a little bit of simplification. 128 plus 74. And that's going to give us 1, 2, 8, 7, 4. 202. So 1, 1, 1, 0, 0, 1, 0, 1, 0 in base 2 is the same as 202 in base 10. Because if we're converting from binary to decimal, all we got to do, find those places with the ones and add those values all together. Converting the other direction is a little bit more complex, a little bit trickier. So let's say I want to convert the number, let's say, we already did something with 200. Let's do 157. 157, transfer that from decimal into binary. So the way that we can do this is we can find the largest power of 2 that fits into here. So our secret next power of 2 is 256. So this power of 2 is too big. So the biggest power of 2 that fits into 157 is 128. So we will mark a 1 in the 128th place. And then we will subtract 128 from 157, which gives us, oh boy, howdy. 7 minus 8 is going to give us 9. So 29. Is that math right? Does that line up? That seems right. Just pull out a calculator real quick because I am frustratingly bad at mental math. I'm good at math, good enough to do this. So our value is 29. So we're going to move right along our sequence, finding the next largest power of 2. So 64 will not fit, so we put a 0 in that spot. 32 will not fit, so we put a 0 in that spot. The next biggest is 16. So we put a 1 in the 16 spot. And then we subtract 16 from 29, giving us 13. The next biggest thing that fits is 8. So we put a 1 in the 8th spot, subtract 8, gives us 5. The next biggest thing that fits is a 4. 5 minus 4 equals 1. So 2 does not fit. And then 1 does fit. So 1 minus 1 equals 0. So once we've reached 0, we know we have made our goal. So our end result is 100,11101 in base 2. So that is our other direction conversion. No, let's see that. All right, if we are going to be encoding a value being binary, the biggest encoding mechanism that we learned about was ASCII. So our ASCII gave every single number, every single letter, every character that we can type a value. It gave all of them a number. So we actually pull up my little ASCII table. So here is an ASCII table, although usually if you're asked a question about the ASCII table, you're only going to have to look at a small subset of this. So we can represent any character, any letter, any number, any symbol using some decimal or hex or binary value. So we can look at our table. If I see the letter D, that is represented by the number 68 in decimal, which we can then convert to binary, or vice versa. If we're given a binary value, can you use this table to find what the proper encoding is? That's what one of the quizzes that we're going to do today is going to have in store. Go back to our other tab. That was this tab. All right, storage size. So here is talking about how many different values you can store based on the number of bits you have. Remember that a bit is just a single digit from a binary value. Bit is short for binary digit. So if I have 4 bits, how many values can I store? So I can store 0, 0, 0, 0, store 0, 0, 0, 1, 0, 0, 1, 0, and so on. I can store up to, let's use our values, we can store 1, 2, 4, and 8. So the biggest number that we can represent here is 8 plus 4 plus 2 plus 1, which gives us 15. So we can represent any number between 0 and 15, which is a total of 16 values. So 4 bits is 16 values. What happens when I add another bit? What's 5 bits? How many values can I store now? Check. All right, I have a guess for 25. So what values can I represent using 5 bits? Let's do that calculation. So I have 1, 2, 4, 8, and my next digit is the 16s place. So the biggest value I can store here is 16 plus 8 plus 4 plus 2 plus 1, which is equal to 31. So I can store any number between 0 and 31, which is a total of 32 values. So with 4 bits, I had 16. With 5 bits, I can store 32 values. Let's go down to 3. Let's see what we could store with 3 bits. So let's clear off those. That's only 2 bits. That's not how this works. 4, 0, 0, 0. So the biggest value we can store with 3 bits, 4 plus 2 plus 1, 4, 5, 6, 7, which is a total of 8 values. So 3 bits is 8 values. So what pattern do we see here? What's the relationship between 8 and 16? And the same relationship exists between 16 and 32, right? So what is my relationship there? It's doubling every single time. So the difference between 3 bits and 5 bits, what's the difference between 8 and 32? It's 2 squared, right? We have 4 times the number of values. So if we have any 2 values of bits, x and y, so 2 to the x versus 2 to the y, whatever the difference is our is how many more values we can store. So let's assume that y is greater than x. The difference in number of values is always going to be 2 to the y minus x more values. Or 2 to the y minus x times more values. Because we have 8 times 2 squared equals 32. So if we go to 6 bits, we double 32, we can store 64 values. What is the relationship between 8 and 64? 8 times 8 is 64, and 8 is equal to 2 squared, or 2 cubed. So once again, we see 6 minus 3 equals 3. 2 cubed times as many values. So our total difference, write that a little bit better, is always, if y is bigger, assume y greater than x, the difference between them is always going to be 2 to the power of y minus x times as many values. So 2 to the y minus x times as many values can be stored in a binary value with y number of digits. Does that make sense? Roughly? Okay. I will save this screenshot as well. Clear, go to the next. So during our data unit, we discussed how we can store images in our computers. So we store images using pixels. And a pixel knows I have a picture. Pixel knows where it is in the picture, it knows its coordinate, and it also knows what color it is. So what values do we use to represent the color of a pixel? What are the 3 things that we know to represent a color? RGB, absolutely correct. So we have a red, so I can use my different colored pens. We have our red value, we have our green value, and we have our blue value. Now, each of those is going to go anywhere between 0 and 255, with 0 being add no color, 255 being add a lot of color. So when I add more colors, we're going to be getting closer and closer to white. So an RGB, let's do a little table. Let's say we have 0, 0, 0. What color is that going to give us? Yeah, if we're adding a whole bunch of no colors, we're going to get black. If we add up, let's say we have 100 of each, what color are we going to get there? So if we're not adding the maximum value, 255, we're not going to reach white quite yet. This one's going to give us a gray. But if I add 255 of each, that's going to give us white. And then our other main colors happen when we add all of 2 colors and none of a third. So let's say we have 255 of red and green, 255 of red and blue, and then 255 of green and blue. If we add up a whole bunch of red and green, we are going to get yellow. If we add up a whole bunch of red and blue, we're going to get fuchsia. And if we add up a whole bunch of yellow, or not yellow, green and blue, we're going to get, I don't really have this color pen, but we're going to get cyan. I guess this is close enough. All right, cyan. So those are the colors that we can get from combining all of those colors. But there's a huge different spectrum of colors available that we can get by mixing and matching small amounts of each of these colors. So that is what RGB is for. That is how we can store large amounts of data. That's how we can store all of our colors using numbers. So every pixel in an image knows its RGB value, and when we combine it all together, we get an actual picture. All right, during our unit, we talked about compression. So what were our 2 different types of compression? Does anyone remember?
Was it lossy and lossless?
Absolutely correct. Lossy compression and lossless compression. Line was horrible. There we go. Lossy and lossless compression. So what are some benefits? Let's look at lossless first. What are some benefits of lossless compression? think the biggest benefit of lossless compression is that we can perfectly, that's how I spell perfectly, we can perfectly recreate our compressed whatever it was. Where in lossy, we don't have a way to perfectly recreate. We can't uncompress to the exact same thing because we've lost some data. However, as an addendum to this, often this doesn't matter. Because we're often going to lose things that we couldn't notice in the first place. Things like audio that we can't hear, or colors that aren't really different enough from the next one to matter. So, lossy compression, often we don't care that we're losing data because we can't tell the difference anyway. Lossy compression also has the benefit of compressing much more, much better compression. Because if we have less stuff to compress, if we're losing data, we're obviously going to be able to compress it much more easily. So not as much space saved. And lossy compressions are also usually going to execute more quickly. So there's our just kind of overview of lossy versus lossless compression. Algorithms or ideas. In general, we're gonna be using lossy compression because A, we don't usually care about the stuff that we're losing, and B, we get way better compression. We can store way more things in the same amount of overall space if we're using a lossy compression algorithm instead of a lossless algorithm. It lets us make better use of the space that we have. So lossy compression is usually the way that we want to go here. And our last little topic is metadata. So metadata is information about our information. So metadata, data about other data. So let's say that I take a picture on my phone. So if I take a picture on my phone, what things are going to be the data for this picture? What is my phone going to store about the actual picture? Like what information is necessary? So I will be storing using binary, but what is the binary going to represent? What picture data is being stored? I think all that we're storing is the RGB values for all the pixels. So the data about my picture is just storing that actual picture. Now, what is the metadata for this picture? What kinds of things might my phone store about this picture. What kind of information might we want to know or need to know?
Would it be the date and time?
Date and time, absolutely. So the date and time when the photo was taken. So that's information it's not the picture itself, it's not the RGB values, it's information about that picture. So the date and time, maybe where I was, so the location, where it was taken. So things like that are the information about the information that we're storing. So the metadata for the picture is all that kind of stuff. So there are questions on the exam that will ask you about both data and the metadata about this data. So we're going to be doing a few different little practice ones today. I'm going to, if we look at, all right, I'll clear this off. So we're going to actually be doing 3 little quizzes: drawing insights from data, changing bits, and encoding data. Those second 2 are only 5 questions long. They're pretty short. Drawing insights from data is the quiz that's asking about how data is being used, how metadata is being used, all that fun stuff. So we will, we're going to start our next class with a discussion of any of the more confusing questions out of here or the other 2 quizzes. So yeah, be prepared for that when we get to it. This is 6 questions long. I apologize. I thought it was 5. So yeah, question number 1.2.4 is 5 questions long. 1.2.5 is 6 questions long. And then 1.2.3 is 15 questions long. So I'm going to ask you guys to have those finished before our next class so that we can discuss them at the beginning of class, answer any questions, clear anything up that might not be super clear. But yeah, any questions on what you guys are being asked to do before we get to next class? Or any of the topics we talked about before? That all make sense? Alrighty.